we're going to dive into the hidden world of engineering. We're talking about the invisible forces that hold absolutely everything together, from the chair you're sitting on to the tallest skyscraper. So let's get into it. Just look at this. At a glance, it's a steel joint, right? A bunch of beams and bolts. It looks totally solid, completely still. But what you can't see is that inside this chunk of metal, and inside every structure around you, there's a constant invisible battle going on. A fight against forces that are trying to stretch it, crush it, and twist it, 24/7. So what's really holding it all together?
And that leads us to the big question for today. It might sound like some kind of superpower, but engineers really can see these invisible forces. They have this kind of, this secret sight that lets them design things so they don't break. And today, we're going to learn exactly how they do it.
That secret sight, it actually has a name: mechanics of materials. This is the field that gives us the tools to understand the secret life of an object, what it's going through on the inside when it's being pushed and pulled from the outside. So what does that actually mean? Well, at its heart, mechanics of materials is all about figuring out how things react on the inside to forces from the outside. It's not just about asking, will this bridge stay up? It's about knowing what every single little piece inside that bridge is feeling. This is the bedrock of engineering, making sure the stuff we rely on every single day is safe. Now, to understand the inside story, we have to start with the outside story. This is where we talk about all the things pushing and pulling on a structure: the world of forces, loads, and supports. First up, loads. A load is really just any outside force that's acting on an object. It could be the weight of a heavy snowfall spread out across a whole roof. That's what we'd call a distributed load. Or it could be the tiny focused force of a hammer hitting a nail. That's a concentrated force. And these loads kind of come in two flavors. You've got surface loads, which are the obvious ones, things that are physically touching the object, like wind blowing against a sign. But then you have body forces, and these are a bit sneakier. They act on something without even touching it. The most famous one, of course, is gravity, that constant downward tug on every single molecule of a structure. So if loads are doing all the pushing and pulling, what stops everything from just flying away? Well, that's where supports come in. They provide the reaction forces that push and pull back. A simple cable, for instance, can only pull in one direction. But a fixed support, think of a flagpole stuck in concrete, that thing fights back against forces from the side, from above, and it resists any attempt to twist it. That twisting force is what engineers call a moment. And here's what it all looks like in the real world. Every beam you see here is being pulled down by gravity. That's a body force. At the same time, it's connected to other beams and to the ground. Those are the supports, providing all the reaction forces. It's this incredible, complex dance of pushes and pulls happening all at once. So, with all that dancing and pushing and pulling, how does it all not just collapse into a heap? Well, that brings us to one of the most important ideas in all of engineering, this amazing balancing act called equilibrium. Think of it like a perfectly still seesaw. Equilibrium is when all the forces pushing and pulling on something completely cancel each other out. And just as important, all the twisting effects, all those moments, cancel each other out too. If a structure is in equilibrium, it's not moving, it's not speeding up, and it's not spinning. It's just stable. And these are the two golden rules that make stability happen. Now, don't let the weird symbols scare you. All they're really saying is, 1, all the forces, up, down, left, right, have to add up to 0. And 2, all the twisting forces, clockwise and counterclockwise, also have to add up to 0. If you can make a design follow those two rules, you've got a stable structure. It's that simple. Okay, so we've covered the external story, the loads pushing in, the supports pushing back, all in a perfect balance. Now it's time to use that secret sight we talked about and finally take a look at what's happening inside the material. So how in the world do you see an invisible force? Well, engineers have this brilliant little thought experiment they use called the method of sections. What they do is imagine taking a knife and just slicing right through a part of the structure, exactly where they want to see what's going on. It's a really powerful idea. First, you make that imaginary cut. Then, in your mind, you pull the two pieces apart. And finally, you just look at one of those halves. By doing that, you've suddenly exposed all the internal forces that were holding the two pieces together. And this is what you see. Once you've separated that piece, the forces that were totally hidden deep inside are now right there on your diagram. You can see them, you can measure them, you can calculate them. These are the forces that the material itself is creating to keep from being ripped in two. And that internal resistance, that fight, spread out over the area you just cut, that is what we call stress. It's the measurement of those internal forces raging inside the material. And that's the answer. That is how engineers see the invisible. They calculate the stress. So why go through all this trouble just to find the stress? Because understanding stress is literally the difference between an incredible design and a catastrophic failure. Let's put all the pieces together. This is where it all clicks. By using that method of sections, an engineer can figure out the exact stress on that single bolt on the left. And by making sure that one bolt is strong enough to handle its stress, they can guarantee the safety and stability of the entire building on the right. The biggest structures depend entirely on the smallest parts. And that's really the key takeaway here. Every bridge you drive over, every building you walk into, even the chair you're on, exists because an engineer understood this relationship. They figured out the outside loads, which let them calculate the inside stress, and then they picked a material tough enough to handle it all. So the next time you look at a skyscraper, don't just see glass and steel. Try to see the invisible ballet of forces, the loads, the supports, and the stress holding it all together in that perfect, delicate balance. Now that you know the secret, what are you going to see differently?